One of the fundamental principles of physics, angular momentum, is one of the most important quantities that describe rotational motion in classical mechanics. Measuring this quantity is especially important in orientation and navigation technologies. For this purpose, gyroscopes were invented. In this video, we will learn how this measuring device, which operates on simple mechanical principles, works. First, we will look at the working principle of the classical gyroscope, then the logic of the MEMS gyroscope used in electronic devices, and finally, the fiber optic laser gyroscope, which provides high precision. Good luck! A classical gyroscope operates using angular momentum and torque. For this, we first need a freely rotating disc to create angular momentum. We know that angular momentum is calculated as the product of the moment of inertia and angular velocity. From this relation, we can understand that a rotating disc is preferred because, thanks to its high moment of inertia, it can produce greater angular momentum. In addition, a rotating body experiences a force directed toward its center. This force is called centripetal force and can be easily derived from Newton's laws. To allow this rotating disc to indicate the direction of another body's angular momentum, it must be able to rotate freely. Therefore, to ensure that the disc maintains its orientation without being affected by the motion of another body, it is mounted on rings called gimbals. Usually, two gimbals are used. One rotates in a plane, and the other in a perpendicular plane. Thanks to this gimbal system, the inner disc has 3 degrees of freedom. In other words, it can freely rotate in all directions in space and maintain its orientation. Now let's see how it preserves its orientation. Suppose you gave a gyroscope disc angular momentum and wondered if it could resist gravity when placed at an angle. In this case, gravity acts on the disc, and because the forces on the particles at the lower part of the disc oppose each other, their effect decreases. As a result, the particles tend to shift sideways, perpendicular to the rotation direction. However, since the particles are bound to the system, this tendency is transferred to the whole system, and the gyroscope begins to perform a motion called precession. This motion prevents the gyroscope from immediately falling to the ground due to gravity. But when friction reduces the angular velocity below a certain level, the gyroscope eventually tips over. This threshold depends on the ratio between centripetal force and gravitational force. The same motion can also be explained with torque. Torque is defined as the vector product of the force and the position vector from the rotation axis. Looking at the same case, torque is perpendicular to both gravity and the gyroscope disc's angular momentum. Therefore, the gyroscope begins to rotate in the direction of the torque, and this motion is called precession. As a result, when you try to rotate the disc in a certain direction, instead of turning in that direction, the gyroscope shifts its axis in another orientation. This side escape makes it appear as if the gyroscope stubbornly maintains its orientation. What actually happens is that, due to the vector nature of angular momentum, the applied torque and the change of axis are perpendicular to each other. Another type of gyroscope is the micro-electromechanical system gyroscope used in electronic circuits. This gyroscope is an electromechanical system designed to measure angular momentum magnitudes in devices such as phones, computers, airplanes, and ships. The system consists of capacitors, a mass, and springs. The sole purpose of this system is to calculate the Coriolis force acting on a moving object inside a rotating system relative to the rotating observer. The Coriolis force is not a real force. It is a fictitious effect that appears when observed from a rotating reference frame. For a stationary observer, a moving object continues along a straight path. But for an observer in a rotating frame, since their coordinate system is constantly changing direction, the path of the object appears curved. Mathematically, this force is expressed as: here, omega is the angular velocity of the system, and v is the linear velocity of the moving object inside the system. Remember, this force exists only relative to the rotating observer. To use this force in our gyroscope system, we need a constant linear velocity. This linear motion can be provided to a mass using a mass spring system. The next problem is how to measure this force electronically. The answer lies in the fact that the voltage stored in capacitors depends on the distance between their plates. Therefore, plates attached to the spring mass system are placed perpendicular to the motion. In this way, The gyroscope in the rotating system is affected by this force, causing it to move perpendicular to its linear motion. This movement changes the distance between the capacitor plates, and thus the Coriolis force is measured indirectly. Using this, angular velocity can be calculated. This system does have weaknesses. After all, it is a mechanical system, so it has limited sensitivity, wears out quickly, and may suffer from synchronization issues. So engineers built a new technology that is fiber optic gyroscope. As the final type, let's look at the fiber optic gyroscope. Unlike the previous types, the fiber optic gyroscope measures angular velocity without the need for mechanically rotating parts, using the interference pattern of two light beams. A laser source is split into two beams by a semi-transparent mirror and sent in opposite directions through a circular fiber optic cable. After completing their circular paths, the beams recombine at the exit. If there is no phase difference between them, no interference occurs. But if there is a phase difference, an interference pattern appears. So how does this phase difference occur? Let's assume our gyroscope is rotating with some angular velocity. As a result, the two beams traveling in opposite directions through the circular fiber optic cable will experience different path lengths. One beam will travel a shorter distance, while the other will travel a longer distance. This path difference creates a phase difference. The higher the angular velocity of the gyroscope, the greater the phase difference. The interfering beams form an interference pattern, and by measuring the path difference between the dark and bright fringes, the angular velocity can be determined indirectly. Thanks to their high precision, fiber optic gyroscopes are used in systems where angular velocity is critical, such as scientific experiments or precise navigation systems. So gyroscopes work like this. From airplanes to submarines, from satellites to scientific experiments, gyroscopes can be reliably used in every field where orientation and navigation are critical. The journey of gyroscopes is a great example of how science shapes technology. See you in the next video, and remember, knowledge is liberty.